So now this section we're going to go into a bit more detail on how sequence numbers are implemented and then increased as segments go back and forth between devices, and how sequence numbers relate to the acknowledgement numbers that come back. So let's dig into that. First of all, a couple things that are useful about Wireshark if you're using Wireshark as your packet capture mechanism. And I mentioned these earlier in an earlier video. Wireshark by default will show you what's called relative sequence numbers. In other words, Wireshark says, look, I don't care about what the initial sequence number is, that big monstrous random number that TCP is actually using. I'm not going to look at that. Wireshark says, look, I know that TCP counts every single byte in a segment. So as an example, let's say that TCP randomly comes up with the number 10 for its initial sequence number. And then it says, okay, in this first segment, there's 10 bytes. So it says, okay, I'm going to count that as byte 11, 12, 13, 14, 15. So the very last byte is going to be byte number 20, right? Because it started out with the initial sequence number of 10. There's 10 bytes in there, so that last byte will be 20. So guess what? When it sends out the next segment, it will start with sequence number 20. If it had randomly come up with the initial sequence number of 9,055, and there were 10 bytes. 9,055 plus 10 would be 9,065. That would be the beginning of the next sequence number. So every single byte is sequenced inside of a TCP segment. The trick is that that very first sequence number is some really big random number. So the nice thing about Wireshark is it does relative sequence numbers. In other words, in the very first segment, it'll say sequence number is 0. Because Wireshark will recognize, hey, regardless of what that random initial sequence number is that he actually came up with, there's nothing in here. There's no bytes in here. And then if Wireshark says, okay, here's the very first segment, and the end, it's got 10 bytes in it. So once again, Wireshark will say, all right, well, I don't care what the initial sequence number is or sequence number before. The next segment, Wireshark is going to say, begins with 10. There were 10 bytes in the previous one. So I'm going to tell you the number 10. So in other words, it's relative. It says it's relative to the actual number of bytes that Wireshark is counting. Wireshark just ignores the actual real sequence numbers, those big numbers, and Wireshark just counts the bytes. And that's what displays for you in the output. As I mentioned earlier, though, if you want to see the real sequence numbers, you can go to Edit, Preferences, Protocols, scroll down among all the protocols, select TCP, and then uncheck the relative sequence numbers box. And by doing that, you'll now actually see the real sequence numbers like these, really big numbers right here, which can be difficult to work with. In reality, seeing the relative sequence numbers is probably easier to work with, but this is good from an explanation standpoint just to see how the numbers actually work. The other thing I want to show you is another Wireshark thing. To follow a single flow, all you have to do is select any packet within that flow and then select Statistics, Flow Graph, and TCP Flow. So for example, right now I've got a filter. I'm not sure if you can see this or not. It's probably very small. Let me just make it a little bit bigger right now. So this is the filter that I currently have on my Wireshark. It's basically saying IP address equals, and I give it an IP address. So this is saying only display for me packets with this IP address. I don't care if it's the source IP address or the destination IP address. Any packet that has this IP address in it, display for me. And TCP. So I don't want to see ARPs, I don't want to see DNS, I only want to see TCP packets that have this IP address in the source or the destination. And so with that, it's pretty easy to follow this flow. But let's say I didn't have that filter. Clear. So now we see all kinds of stuff in here. Most of it is between my two devices. Is there any other stuff in here? Well, let me just do another capture real quick. Okay, so here's a whole bunch of stuff going on. I'll just open up another web page. There I'm opening up a page to Google, and how about a page to my local news here in Raleigh, WRAL.com. Okay, so I've just done a whole bunch of stuff. Stop the capture. Now if I was looking at this and I said, okay, I only want to follow the flow between these two devices. You know, there's a lot of stuff in the middle here, DNS from other stuff, ARP from other stuff. I only want to follow this flow. Well, I can click on a packet, any packet in here, and then select statistics. And about 3/4 of the way down here is flow graph. And then select TCP flow. And hopefully it will come up. Here we go. And I'm not, hopefully you can see that fairly well, but it actually shows you IP addresses. So for example, I know that 10.7.1.101 is me. So I can see everything between me and 173.227. Now in this particular case, if I minimize this, I was interested in 199.83. 199.83. So if I go back to that flow graph, where is it? So 199.83, where are you? I imagine it should come up here, unless, oh, here we go, I just have to expand it. So this is showing me all of the TCP flows. I can just scroll, where's 199.83? Here it is, 199.83 is this column right here. All right, so right here, that looks like it's my very first packet from myself to 199.83.132. And when I click that, it actually highlighted it in here. And you can see that is my sync right there. So now if I keep going down, okay, where's the next one? Right there. So there's the next one on that line. So that would be the sync plus ACK. That would be the ACK. And so now everything terminating on this dashed line here is part of the TCP flow between me and that device. Now, I don't know if you can read it, but on the left-hand side, it's giving me the actual timestamps of the packets. And on the right side, if I can increase this a little bit, it gives me the sequence number and the ACK number for each one of those. So this is kind of interesting to follow the flows of your TCP traffic. Oh, and also, one thing I did wrong here. Let's go back. When I selected my packet, I did statistics, flow graph. In addition to selecting TCP flow, if I only wanted to see that one flow, because I was seeing everything, right? I was seeing all the TCP flows. I could have selected displayed packets, which is just the one I clicked on. Displayed packets. Well, it's still showing me the same thing. I suppose I'd have to create some filters first to filter out all that other traffic to then just see the TCP between these two. But it gives you a good idea as far as how many flows you've got. I mean, look at my particular example here. These are just TCP flows, and I've got a lot more than I expected. Because I've only got about 4 websites open right now, but look at all these destination addresses that I've got TCP connections going to with just that 5 seconds of sniffer traces that I did. All right, so let's go into the section here on sequence numbers. So when the TCP syncs, so the first part of the 3-way handshake, we mentioned it's going to start out with some initial sequence number, which is going to be a huge 4-byte number in size. No way to predict what it's going to be. Now the server, the other end of the connection, he's going to come up with his own sequence number because it's a bidirectional communication. Both sides have sequence numbers for every byte. And in his sync plus ACK, notice what he's doing. Whatever my initial sequence number was, he's taking that number and adding 1 to it. And then same thing, I take his sequence number of Y, and when I acknowledge it, I add 1 to that. Now at this point, no data has been sent. So what are some key takeaways? The initial sequence number is a random value. And this is also important. The sequence number in segment Z. So if you take any segment in TCP stream, maybe it's the 200th segment. So whatever that segment is, we'll call it segment Z. And that segment's going to have some sequence number in it. That sequence number is a byte count, but it does not include the bytes in that segment itself. That sequence number represents all the bytes previous to that segment. So all bytes sent up to but not including segment Z. Let's see another example of this. So let's say, for example, that in my TCP sync, I start out with a sequence number of 5333. Well, the server's going to say, okay, I expect 5334 next. Now let me just pause here for just a minute. Let's say currently, I don't know what segment this is. Let's just say this is segment number 134. It really doesn't matter, just have to put in some number. And let's say at the beginning of this, I have sequence number 2444. And then we'll make it small. 1, 2, 3, 4, 5 bytes in the actual body of this. So as TCP counts this, it's going to say, okay, that first byte I'm going to count as 2445, 2446, 2447, 2448, and 2449. So the next time I send a segment in that same direction, so this is going to be segment number 135, guess what? It's going to start out with sequence number 2449. So whatever the sequence number was of the very last byte in my last segment, that's what sequence number I'm going to start out with right here. And so when the ACK between these two, ACK for segment number 134, he's going to ACK 2449. He's going to ACK that, 2449. So 5333, 5334. So in this particular three-way handshake here, there's no data. There's no bytes to speak of. So this is where we really get into it. So the three-way handshake is done. Sync, sync, ACK, ACK. So number 3 here was the ACK, the last part of the three-way handshake. And at this point, I had sequence number 5334. So now in the next one, this is the first data I'm uploading. You know, maybe I'm doing a file upload or something, or maybe this is my HTTP GET or whatever it is. Notice I take the sequence number of here and copy it into here. You might say, well, why is that? Well, because this didn't have any data. This last ACK, there was no data in it, so there was no reason to increment this number. You only increment the number in your next segment if there's some data that you're counting in the previous segment. Well, in this segment here, there was no data, so we kept the same sequence number. Let's take a look at that also in Wireshark. Okay, so in this particular case, this is where I was doing a telnet. Where's my mouse? Right here. I was doing a telnet into INE's racks. Move this out of the way. All right, and the telnet is right here. So now what I want to do is I want to put in a filter. I only want to see that telnet traffic, 75.140.41.66. Okay, so here's what I want to show you. Sync ACK. Okay, so here's the final ACK. So this is for me going up to INE's racks. Now notice in this particular ACK, look at the sequence number. Huge number, but just pay attention to the last 4 digits, 9270. Now in this particular ACK, there's no data. It's just an ACK, there's no data. So in the very next segment I send, going to 75.140, it should end with 9270. The sequence number should be the same. Let's see, where's the next one I send? Let's see, yep, right here, 9270, and we can see sequence number is 9270. Actually, I think what was a better example was all right, I'm not able to pull up the capture that I was looking for, but here's the point I was going to make. If this is an acknowledgement, and I'm acknowledging some sequence number, it really doesn't matter what it is. Every TCP segment, no matter what it's carrying, even if it's just an acknowledgement, has a sequence number. So this is simply TCP ACK, no data. So here comes some data, here comes some data, and once again, I send another TCP ACK, and this time I'm ACKing, whatever it is. My sequence number will still be the same, because the last time I sent something there was no data. And now here's some more data coming down from the server, and once again I send another ACK, and you're going to see the sequence number is still the same. Throughout this whole process, even if I end up sending 2,000 acknowledgments to him because he sent me 2,000 segments, every single one of my acknowledgments going upstream is going to contain the exact same sequence number because there's no bytes that I'm counting. And that's the thing I wanted to reinforce here, is that the sequence number is counting the bytes in a segment. And if there's no bytes to send, it remains static. So let's look at this one. TCP segment's going up. It's 5334, but it contains 50 bytes of data. So that means the first byte is going to be 5335. The second byte is going to be 5336. So if we go to the 50th byte, we're going to have 5334 plus 50. So that means that my next segment, should be 5384. The next segment I send upstream is going to be 5384. And this number here is the number of the 50th byte, the very last byte in that segment. And so the acknowledgement, when the acknowledgement comes back, the acknowledgement is going to say, okay, I saw 5384. And there it is, acknowledging 5384. Now let's actually see this in a sniffer trace, and then we'll be done with this section. Let's see here. Okay, so we'll do this one here. Okay, so here's my initial sync. ending with 9927. So that was my initial sequence number, ending with 9927. Here comes the sync plus ACK. Now this is kind of interesting. Notice this. Now the sync, is there any data in this very first segment? No, there's not. Just a TCP header by itself with the sync flag set. So normally you'd think, okay, well, there's no data in here. So just like an ACK that has no data, there's no reason to increment the sequence number when we send the next segment. And yet look at this. We go from 9927, and then the next segment I send, which is my final ACK, is 9928. Why did he increase it by 1 byte? There wasn't 1 byte of data in here. And this leads to a concept that you might see sometimes. Whenever there's a segment that contains a sync or a segment that contains a fin, it's sort of, and I haven't been able to find the reasoning behind this, but I'll just tell you what it does. TCP basically sort of pretends like it's carrying 1 byte of data behind it, and you'll see that referred to as the phantom byte. Yeah, kind of weird, but it's called the phantom byte. So in this particular case, my TCP sync didn't really have any data in there. There was no reason why it needed to increase the sequence number for the next segment, but it said, well, I'm going to assume there's this phantom byte here, and so I'm going to increase it by 1. And that's what he did. The next segment went from 9927 to 9928. But notice this right here, this third one, if I scroll down. Remember, I said only if there's a sync or a fin do we add that phantom byte. Well, this third, remember, sync, ACK, sync, sync plus ACK, ACK. So this is just an ACK. So the sync bit is not set, nor is the fin bit set. So because neither one of these are set and there is no data here, this sequence number of 9928 is then going to carry over into the next segment. And here we see it, 9928. Now let's do a little bit of math here. So 9928, let's bring up our calculator. Okay, I'm not going to do the entire number. We'll just do the last 4. 9928 plus this segment has 1,191 bytes, 1191. So if we add that to it, 1191 equals, that means that the very last byte in this particular segment has the sequence number of, well, it actually says it right here, 1119. That's the very last byte. So now we get an acknowledgement saying, okay, I saw that very last byte of your last segment. Now, so it was, the next segment should be 1119. So if we scroll down here, where's the next one from 1.101? Here it is, and it is 1119. Now this doesn't have any data. It's just an ACK. There's no data in it. So there's no reason to increment the sequence number. We're going to retain the sequence number on the next one. So 1119, and guess what? Here's the next one, also 1119. This is also an ACK. No data in it. So you're going to see here from this point on, every single time I send an ACK, it's just going to stay as 1119. And my sequence number here is not changing at all because I'm not sending any data. If I'm not sending any data, there's no reason to increment it. Now let's look at it from the perspective of the server that was downloading stuff to me. So sync plus ACK. Okay, so now here, the server said I'm going to start out with initial sequence number of 0214. Now the sync bit is set, which means that phantom byte is in there. There's no real data at this point, but we're going to add that phantom byte. So we're going to say, all right, well, that phantom byte would have a sequence number of 0215. And sure enough, right here, that's what he gives the sequence number of his next one. Now this one right here, this is just an ACK. There's no data in it. So he says, okay, now this is the 54.84. That's the server talking to me. So the server says, okay, 0215, it's an acknowledgement. There's no data in it. So the next time I send something, I'm going to retain that sequence number. So here's the very next one, 0215, 0215. Now this has 1,460 bytes of data. So once again, if we do our math, ending with 0215, and we add 1,460 bytes of data, so the next sequence number, the last 4 digits, should be 1675. And actually, Wireshark is smart. Wireshark did this. This is actually not a part of the TCP header. Wireshark is just gracefully saying, look, I've added up the bytes for you. 0215, if I add 1460 to it, the very last byte number is 1675. And sure enough, if we go to the next sequence, it starts with 1675. So the last thing I want to mention about this is that I've read in a lot of places that people say, well, they take a look at this. They say, let's go back to here. Let's take a look at this one. They say, all right, this was the server talking to me, sequence number 1675, and they say this ACK, I'll take a look at the ACK, 3135. Let's compare those two numbers. A lot of people say, okay, well, this is saying I've received all bytes up to, but not including this. A lot of people would say, okay, well, if I was actually counting bytes, the last byte I actually received was 34, and I'm now saying I expect 35 next. Well, that's not actually true, because look, in this segment right here, it started with 1675, and then byte 1 was 1676, byte 2 was 1677, and byte 1460, that byte was 3135. So actually, this is acknowledging the very last byte it received from the very last segment, because each byte is counted in the sequence number.